Hello, and thanks to the VMSG organizers for having me. I'm going to be talking about crystal shapes today. I won't have time to discuss all the details of this treacherous world, but I hope to cover a few pitfalls and opportunities. So let's jump right into it. We start off with this beautiful thin section from a 1980 to 86 Mount Helens dome rock. Let's assume we want to find out more about what happened to the magma during final ascent, and to do so, we will look at the crystal size distribution of the plagioclase microlites. So first, we're going to outline all the crystals. Note that this is only a small part of the total area analyzed. Then we use image processing software to get the distribution of width-length ratios in our sample. This will look something like this, and it shows the number of 2D elongate shapes to the left and the number of 2D square shapes to the right. We can then put our 2D width-length data into a stereological projection program like CSD Slice, which will then give us an estimate for the 3D shape of our crystals. In this talk, I will use the Zing diagram to illustrate 3D shapes, which plots the 3D intermediate to long axis against the 3D short to intermediate axis. In the case of our Mount Helens sample, we get a value of 1 to 1 to 10, which plots down there a long prismatic rod. We may be tempted to take this value and put it straight into CSD corrections. But instead, let's pause and consider whether this shape and the underlying assumption actually make sense. Would we really expect the crystal shape not to vary across crystal sizes? Well, decades of experiments have shown that crystal morphologies do reflect the magmatic conditions they nucleate and grow in. In particular, it's generally considered that higher undercoolings produce more elongated 3D shapes, as shown in this schematic by Shi and Hammer. A lot of this has to do with crystal growth becoming controlled by diffusion at high undercoolings, producing our funky skeletal and dendritic crystals. But it's generally thought that this trend is also true at lower undercoolings, where we may have variations in growth mechanisms. If we now consider that our Mount Helens microlites grew during ascent from a magma reservoir at some 5 to 8 kilometers depth to the surface, and that decompression increases the plagioclase liquidus, we can imagine that this decompression will produce rapidly changing and generally increasing undercoolings. So we expect successive generations of microlites to track these changes in undercooling. With this in mind, let's revisit the backscatter image. Does this stretched rod really represent all our crystal fractions? Well, if I subdivide our microlites into fractions with lengths smaller than 5 microns, 5 to 10 microns, 10 to 30 microns, and 30 to 100 microns, it does look to me like the larger fractions show distinctly tabular 2D shapes, and the smallest fractions show more square outlines. And if you project the 2D width to length distributions for each of these fractions to 3D, we begin to see a clear picture. Smaller plagioclase form more prismatic crystals, and larger crystals have more tabular shape. This trend is true for 5 samples from the 1980 to 86 Mount Helens eruption, and we find similar patterns for the Santiaguito lavas here, and for reprocessed published data from Galeras from Bain et al. So what does this trend mean? Let's first try to correlate our fractions with the ascent scenario they reflect. It's a reasonable assumption that the largest crystals crystallized first and the smallest crystals last. A straightforward interpretation would then be that the large crystals nucleated deep in the conduit and the small crystals in the shallow conduit. We can therefore expect that the crystals nucleated and grew in quite different environments, including undercooling. And we can actually use the number densities for each of the crystal fractions as a qualitative indicator of the undercooling and the evolution of the undercooling, because nucleation rates do increase up to a certain point with undercooling. And we can see, if we look at the number densities per fraction, that there's smaller numbers of large crystals than there are numbers of small crystals. That's kind of a pretty basic observation for anyone who has ever done a CSD, but it's important to point out. At the same time, it means that the total cumulative number density in our magma increases rapidly during ascent. This will be important, but for now let's appreciate that the undercooling is slightly increasing during ascent, and thinking back to the correlation of undercooling with shape, we would expect crystals to become more elongate and tabular, but we kind of see the opposite. So let's think about another way to interpret these shape changes. Could it actually be that this evolution from rods to tablets reflect shape changes during the growth of plagioclase? In other words, did the tablets start as rods before they grew into the tablets? To explore this more, let's do a simple thought experiment. If we have a parcel of magma with a low number of crystals and we want to increase crystallinity by 20%, then each of the crystals will have to grow quite a lot to bring about the crystallinity increase. On the other hand, if we have a large number of crystals, then each crystal will have smaller individual growth volume. Now, this wouldn't matter too much if the shape wouldn't change during growth, but if we assume that nucleating crystals are indeed rods and that they are overgrown by a more tabular shape, then the amount the crystal grows will determine its shape. We modeled how a 1 micron nucleating crystal would change its shape in both low and high number density scenarios, and we can see that our 1 micron starting rod would develop tabular shapes in the low number density case, similar to our largest Mountain Talents crystal fraction here. On the other hand, for high number densities, our starting rod would not change its shape much at all, resembling the shapes of our natural crystals smaller than 10 microns. So this model can explain the entire range of crystal shapes we see in natural samples simply by moderating the amount of crystals. Of course, that's a simplified model, but it does give us some important clues as to what's happening. So let's try to reconstruct how our natural samples have developed the shape and size distributions in the erupted rocks. We start deep in the conduit, where a relatively small number of crystals nucleate and grow to tabular shapes thanks to high growth volumes. This will be our 30 to 100 micron fraction. During further ascent, the next generations of crystals will nucleate in an increasingly crystal-packed magma, and individual growth volumes will be decreasing, so the crystals will become less and less tabular, and the smallest crystals nucleating will be prismatic rods in the shallow conduit. Things are of course a little bit more complex than what I've shown today. We currently have a paper under revision that goes into more detail. We of course don't have time for this though, so I'm leaving you with the conclusions here. Finally, I would like to stress that stereological projection software is not a geologist, so you have to be careful in what data you put in and how you interpret the output. In fact, we have been working on a new program that projects from 2D to 3D, which is hopefully more robust and illustrates inherent uncertainties. Here's a quick glimpse. This will also be part of the paper under submission. So I'm happy to take any questions now. Thank you.